Hey everyone! Thanks for joining us for the next session of AI Apps and Agent Dev Days. My name is Anna. I'll be your producer for this session. I'm an event planner for Reactor, joining you from Redmond, Washington. Before we start, I do have some quick housekeeping. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional, and on topic. Keep an eye on that chat. We'll be dropping helpful links and checking for questions for our presenters to answer. Our session is being recorded. It will be available to view on demand right here on the Reactor channel. With that, I'll turn it over to our speakers for today. Thanks so much for joining.
Hey, everybody.
Hey, everyone. Thank you,
Hey.
Anna.
Thanks. My name is Anthony. I'm from Microsoft, and with me today we've got Stephen as well from NVIDIA. Stephen, do you want to introduce yourself?
Sure thing. Hey, everyone. My name is Stephen McCullough, and I'm an AI solutions architect with NVIDIA. So this means that I get to work with Microsoft on implementing all of the latest and greatest models and AI technology into Azure. So a bit about this program. So Microsoft and NVIDIA have been in close partnership and continue to be in close partnership to power the next generation of AI through deep integration of NVIDIA's computing platforms with Microsoft's global cloud infrastructure. So this webinar series is a big part of that. We really want to work together to show users like you how to best leverage the magic of both NVIDIA and Azure together. So make sure to tune into the series as we explore all of these great integrations and show you how to apply them best in the real world. I'll hand it back to you, Anthony.
Yeah, thanks very much. Yeah, so I work at Microsoft, and I am one of the Python advocacy engineers. I also do a lot of work with AI, and I'm a fellow at Macquarie University, and I do research into AI, in particular in performance is something that I'm very fascinated with, and I've always looked at application performance historically, and now that AI has been such an interesting technology, I've been quite deeply interested in the performance of the AI. So the sort of speed performance, not the quality performance so much. So yeah, let's jump into it. So today we're going to cover off talking about AI performance at a high level. This talk, I'd say, is a pretty technical talk. We're going to get into the details in terms of like the actual AI sort of inferencing and what factors impact model performance. And then we're going to talk about sort of benchmarking the models at the low level, so at the inference level, and then also like benchmarking the actual application. So we'll cover that a bit later. And then the goal here is that we don't just talk about it, but we actually give you some things that you can take home today, and you can kind of apply into applications in your infrastructure. So we're going to talk about what we can actually do to accelerate performance, and then cover off some of the more sort of cutting edge techniques. These are things that I've heard about or have kind of been developed or evolved in the last month, I'd say. Everything with AI is cutting edge. But yeah, some of the stuff we've got here today is kind of very, very recent. So yeah, let's just jump into AI performance. Next slide. So AI performance, kind of in any kind of application performance we're interested in metrics. So we've got performance of the model, which can mean accuracy. So normally if you look at benchmarks for models, it will give you accuracy in terms of answering questions, or its relevance for looking up in the systems like RAG, for example, or how well it can score on a math test or some sort of examination. In particular, on this talk, we're going to talk about performance in terms of speed, because that's another sort of very big topic. So you can look at accuracy for models, you can look at regressions. Accuracy is very good with models because you want to kind of have a baseline so that when you upgrade between different versions of models or you're experimenting with other models, you have a baseline for your application. We're not going to cover that today. We're going to look at serving performance. And with serving performance, we're particularly interested in two things. One is latency, the other is throughput. So next slide. So the measurements depend on the use case. And if you go kind of in the stack, we've got the actual inferencing engines themselves. So this is like the code which runs the model. So this inferencing engine, VLLM is like one example of this. There's some ones you can run locally as well. Like some people might be familiar with like Ollama as like an inferencing engine. Onyx Runtime is one that we work heavily on at Microsoft, and is available also in AI Foundry. So in Azure AI Foundry, you can run the models in infrastructure that's hosted by Microsoft. We've also got other types of models. That's language models we're talking about, so large language models. We also kind of have smaller language models, embedding models, re-ranking models, world generation models. So there's kind of a lot of different types of AI model. And the metrics are more or less the same in terms of you're looking again at throughput and latency. Latency is how long it takes for the model to start responding, and then how long it takes to do the whole response. And then the throughput is how fast it can give you back the information. And we normally measure that in tokens. And then you've got also the applications that sit on top of that. So the next slide. So yeah, I think what's important with AI is, and in any kind of systems performance, is that your users have expectations for what they deem as fast or slow. So if you just build this out, I'll explain it. So I've got my log scale, which is kind of from 10 milliseconds up to 10 seconds. And what I think is that, users, as they use devices, as they learn to use computers as their kids, as they interact with the internet, they have an expectation that when you pick up a phone and you open an app, it will launch the app within 100 milliseconds. And if it doesn't, you would instinctively get a feeling that your phone is running slowly. On your desktop environment, so if you're running Windows or Mac or Linux, and you start an application, if that application takes 500 milliseconds to start, that will feel slow. That's because you've kind of got this intuitive sense of what is fast and what is slow in the context of like your local environment. Then if you're interacting with something that you know is on the network, so like sending a message to somebody, loading up a website, like streaming a video or something like that, you have a different expectation. So like if I open up Netflix and then I start watching a video and it takes a second to load to start streaming, I have that expectation. That's kind of expected. Now with AI, it's kind of different because this is such a new technology. But I kind of do get a sense that users, as they're being introduced to AI, they've got an expectation that it can take a second or more for the AI to kind of respond to a question if they're interacting with it over text or audio. So if we jump to the next slide. So what's important with this is that if you put AI into a feature and the user has an expectation as to how quickly that feature will respond, and all of a sudden it doesn't respond like that, it will feel slow. So for example, this example I use is a where you wouldn't introduce AI without telling the user, or at least giving them the choice, is if they could have a search box on the website where they could type in some keywords, look up a particular product or something and click search. And if you just build that out again, if you just said, okay, we're going to introduce AI to this feature, and every time somebody searches for something, it's going to do like an LLM call in the background, all of a sudden it's gone from a search query, which could be 100 milliseconds for a well-optimized database and then you've added AI, and now it's going to take a second or more. The users are going to get frustrated because if they just wanted to look up a particular product, they already know the name of the thing. They don't need AI in that circumstance. Adding AI and making it 10 times slower is going to be really frustrating for the users. So kind of my big caution here is that you need to kind of factor in the latency of the AI in the context of the application. And so if we jump to the next slide, the AI taking a long time to do something can be fine. And in some circumstances, the user's kind of understanding of why it's doing this is because it's taking time to do something that would actually take them a lot longer to do. So for example, if I said, I want you to go and read, all the leading papers on this particular topic, and the AI comes back to me, sort of as Copilot, for example, and says, okay, I'll do that for you. I'll have a response within a couple of hours. And it comes back after a couple of hours and says, here's all the papers I've read. Here's my summary of your research question. Here's some citations and links you can consider. And it comes back with a report for me after a couple of hours. Like, as a user, I'm fine with that because it would have taken me a couple of days to do myself. And like, it's set the expectation. So kind of what I want to start off with is that, for something to take a second or two is fine, but you need to kind of consider in your application where you're putting that functionality and what is the user expecting the performance to be like. So next slide. So at the top right-hand side is a link to the HAX toolkit, HAX. This is the sort of human AI experience recommendations that we have at Microsoft. And these are the ones that we build into our products. But we also have an open portal, and I've picked out a couple of these that are kind of specific to performance. So don't put AI in the way of an otherwise fast and efficient task. So like keyword search, for example, is something that's very well optimized in databases. Like dropping an LLM into that cycle, like for most users, is not necessarily what they need. They know how to use a keyword search tool. They don't need an AI to kind of like summarize the answer for them. AI can be very good at RAG and ask the user asking a fluent question. Keyword search is bad at that. So that's kind of an example where you would want to introduce AI, but you'd have it as a choice that the user can switch towards. Don't wait for the AI to finish before displaying the answer. If the user types something and they have to wait 1 or 2 seconds until they see anything, that's a bad experience, and people will be confused, or they'll just keep clicking the button again and again. Also, don't use reasoning models unless you need reasoning. It's very tempting to use a reasoning model because they can give really well thought through answers, but you need to consider which model you would use and when. You use AI to enrich features, so improving functionality on the site, but have the option to either disable or dismiss that AI feature if it's something that previously would have worked without the AI. Also, I'd strongly recommend streaming back the results from the AI. Most of these have streaming modes. So once the users type the question, they'd start to get back information. And then if it is going to take, 10 minutes, an hour potentially or more to do like a deep research task, then to have the option to send a notification later on. Next slide. Cool. So over to you, Stephen.
Thank you, Anthony. So these are all really important things to keep in mind as you're planning out your AI inference and planning out your application. But when we really want to get into the nitty-gritty and the details of AI inference performance, we need to get a bit more under the hood and establish some important topics and establish some ideas about how AI generates content. It generates code and text and videos and images. So let's start off, talking about how LLMs work. Really, LLMs auto-regressively generate a single token at a time. So if I put in a prompt that says, make me sound smart, right? We know that it goes to the AI model, it gets fed through the GPUs, and then it comes out with a single token. And this token eventually gets appended back to the prompt and input, and it gets passed through the GPUs again and generates the next token. So after LLM, it might say LLM Inference, and then that entire string gets passed through the AI model again to generate the following token. So the way this is working at a bit of a deeper level is that each of these prompt tokens are being embedded and encoded by the AI model, and those embeddings are being used to generate the next token. So to predict the next token, the LLM needs to examine every single token that has come before it. It needs to compute the positional embeddings and the attention for each of those tokens. it needs to pass those values through its neural network, and then the LLM can finally choose the best single next token. And remember, all of this processing, all of this computation is just to generate a single token. And once that's done, you have to do it all over again just to get the next token. You have to recompute all of the positional embeddings and attention for each of the existing tokens, now including that one that you just generated, and pass those values again through your neural network and generate the second token. So a big part of the values that are generated in this process is the keys and the values for each individual token in the input. So this needs to be generated for every single token that the LLM creates. But here is an important catch. The positional embeddings and the values that are stored in these two matrices, they don't change. So once you generate the keys and the values for the prompt, you don't have to compute them again for every single new token. You really only need to compute these key and value matrices once, and then you can reuse these values for every single new token. So what ends up happening is that you generate these key and value matrices for this input, make me sound smart, and it gets placed into what's called a KV cache. So a bit more about that here. So those key and value matrices are now cached in what's called a KV cache. And these cached values are reused to generate every single following token. So if you remember, we asked the LLM, make me sound smart. And the first token it generated was LLM. Then it passes this entire input again through the GPU, and it generates the token Inference. So whenever we pass it through the LLM, remember we already had these key and value matrices cached and already pre-computed. So we can just use them again in all of the calculations that go into generating this next token. The only real addition to these matrices is the key and value embeddings for this new token that we generated. So because of this KV cache, we can significantly improve how many tokens we're able to generate per second. And still, even if you're only computing these embeddings once, there is an immense amount of computation that needs to be done. So this is why having the right hardware and right model precision and configuration makes a huge difference. So this KV cache is a big part of AI model inference performance. Now, there are two stages that we need to be familiar with when talking about AI performance. The first is what's called the prefill stage. And this is what happens whenever you first submit your prompt to the LLM. And what it's doing is processing all of the positional embeddings and the attention values for each token in your prompt. So this is before it has generated any token at all. Your LLM hasn't output anything yet. It's just processing the prompt that you gave it. So whenever you pass in the prompt, it again passes all of your values through the neural network and stores them in your KV cache. Now, once it has processed the entire prompt, then it generates the first output token. And we call the time between the moment that you submit your prompt to the moment you receive that first output token as the time to first token, or just latency, really. So This entire process is called the prefill process. So whenever you hear latency, think of this prefill process. Really, prefill is just processing the entire prompt, everything given to the LLM before it even generates a token. So as we mentioned, this is a huge benchmarking, or very important benchmarking area for us. So it's something we really need to pay attention to and optimize, because as Anthony mentioned, users are used to a certain amount of latency. We expect a certain amount of latency and throughput, and optimizing this prefill process really helps drive down that latency. So now, once you have completed this prefill process, your entire prompt and context is processed, it's stored in the KV cache. Then your LLM moves into what's called the decode phase. And this phase is pretty much the entire rest of your LLM's activity. So this, in the decode phase, it generates every single sequential token. So once we submit our prompt, it gets tokenized and placed in the KV cache. And then our LLM creates each individual token out of it. So if I ask it to, let's say, tell me about the history of Microsoft, right? The prefill process takes that entire prompt and processes it, stores it in the KV cache, then stores or generates the first token, and then we move into the decode phase. And within the decode phase, every single token that we generate has to be added back to that KV cache so it can be used again to generate the next token. So it is just mind-blowing how much computation is going into just generating a single token. And these models are generating hundreds of tokens per second. So it's pretty incredible what you can achieve with these models. So whenever we're talking about the throughput, as Anthony mentioned earlier, that's the amount of tokens we're generating per second. And that comes down to how efficient your decoding process is. So whenever you hear latency, think of prefill and processing that prompt and all of the context going into the LLM. And whenever you hear of throughput, think of the decoding process and all of the computation going into creating that next individual token. So these are the real two main processes that happen during LLM inference. And it's important to understand these as we sort of talk about benchmarking and improving performance. So another big area that can help improve performance is batching. So whenever you are running your LLM, you could just have it process a single prompt at a time. But whenever you're doing that, you may not be utilizing your hardware to its fullest potential. And in that case, you might be seeing less throughput than you otherwise might be able to achieve. So whenever you are using something called batching, what's going on is you are processing multiple prompts at the same time on the same hardware. So, for example, if a user asks, when was NVIDIA's TRT LLM released? And then, maybe a couple clock cycles later, a different user asks something about document summation. Different user asks, what are the minimum system requirements? Then it processes all of these at the same time in a single batch through the GPUs. So this is really important because it's going to help you utilize your hardware to its fullest extent. Now, there are some trade-offs, and just sending your batch size to the moon isn't always the optimal solution. Really, there's a trade-off between the throughput you can get with higher batches and the latency you're going to see. So we'll talk about that more, but batching is another big area that is important to understand as we optimize our LLM performance. So whenever we talk about LLM performance, it's important to think about how we actually measure it. So we use the almighty benchmark um, to help figure out, what kind of throughput, what kind of latency is our model seeing, and we test that in real time. Now, I'm sure a lot of us have heard of AI benchmarks like Humanity's Last Exam or the AME 25 benchmark, which are really focused on sort of like the model quality and its accuracy and kind of intelligence as we gauge it. So those benchmarks are really geared towards the models themselves, but what we're focused on today is the serving performance and how we can benchmark the latency and the throughput of our LLM models. Now, this is a big part of the model serving process because especially if you're a DevOps engineer or an MLOps engineer, you're probably going to be very familiar with this process. You'll need to test out your models on different hardware, using different engines, using different data sets to figure out really the most optimized configuration for your use case. Now, whenever we are benchmarking, there's a couple things to know here. So we could really benchmark at different levels of our AI stack. If we want to benchmark our LLM engine, we can use NVIDIA's TRT LLM bench to really get in-depth details about what our model is doing and how it's performing. Now, I'll show some benchmarks later on, but especially if you're using something called speculative decoding, TRT LLM bench can really give you some big insight into that. And I'll go more into speculative decoding in a bit. So if we move up the stack, we can measure an LLM endpoint for its latency and its throughput using GenAI Perf or SGLang bench serving, or a variety of different tools out there that really all are focused on measuring the endpoint performance for an LLM. So these are very versatile because whether you are running the LLM locally on a VM, and whether you are running it in Azure or on a VM or on AI Foundry, this is really going to allow you to benchmark across all of those use cases. So there's lots of versatility here. Now, moving up the stack again, whenever we're benchmarking our AI application, that's where something like Azure load testing is going to be super, super helpful. Because, if you've ever built an AI application, it's of course not just a, easy front end and then an AI endpoint in the back end. There's lots of computation, probably database reads and database writes that are going on behind the scenes that your application needs to be benchmarked for. So really, if you want to have a comprehensive idea of how your AI application is performing, it's very helpful to cover all of these bases here. Now, whenever you're benchmarking your application or benchmarking your AI model in general, what's happening is your tool is going to be sending in example prompts to the model and measuring how fast it's generating tokens and how long it takes to generate that first token. So the data set that you're using, those prompts that you're using, is very, very important here. Really, as a best practice, if you can, perfectly mimic the kind of prompts and data that users are sending to your model in production, if you can mimic that in your testing and your benchmarking, that is fantastic. You really want to be like, in an ideal world, you could perfectly mimic the data being sent from your users to your LLM in your benchmarking environment. Now, that's not always possible, but you can at least sort of narrow it down, starting off with the data types, like whether your users are sending text or code or images or videos. You can control what's called the sequence lengths, which is essentially how many tokens are being sent by the user. You can control the different requirements and prompts and temperatures and parameters that are being sent by the user. So there's a lot to keep in mind here whenever you are benchmarking. Now, again, the real end goal of that is to be able to have a data set that matches the production data as closely as possible, so you can get real numbers with your benchmarks. So I have a couple demos here that I wanted to show you about benchmarking. So yes, okay, perfectly. You can see my screen. All right, so whenever we are talking about benchmarks, I wanted to show you some of the processes that we use. So let me go ahead and start up a TRT LLM container. All right. So now I'm in my TRT LLM container, and I'm going to use TRT LLM serve to serve an open model. So the model I'm serving is Mistral 7B Instruct version 0.2. And this is an open source model that you can just download directly from Hugging Face. And TRT LLM is also open source, so you can replicate this stack very easily. So what it's doing right now is TRT LLM is going to it's going to load the model weights into the GPU. Right now I'm using a standard NC40 virtual machine that's on Azure, which has a single NVIDIA H100 GPU with NVLink on it. So very capable hardware. And we're going to see, what kind of throughput, what kind of latency we can get when running this model. So it takes a couple seconds to load, but it's in addition to loading the model weights into GPU memory, it will establish the API server in front of that model so that we can just directly hit an API endpoint and interact with our model. So this endpoint isn't just going to establish, somewhere that we can send chats to, or somewhere we can use for inference, but it's also going to provide data such as the API spec for this model. It's also going to provide data around the models that are available. So really, TRT LLM is setting up a lot in the background that's going to make this completely ready to go, completely ready for testing and production. So right now it's creating, you'll see it's prefetching some of the weights, it's loading the weights and establishing the CUDA graphs. And we'll see in just a second here whenever it's ready to go. And you can download this exact container directly from NVIDIA's website. So if you just search TRT LLM container, you'll find it pretty easily. All right, so it has established this endpoint locally. So I can come over here and I'm going to benchmark it. Well, first I'm going to just make sure that everything looks good. I'll submit a health check. So first of all, note how fast that was. Note that, all of that computation that we talked about earlier, all of that KV cache and embedding and encoding and just matrix multiplication that it took just to generate a single token, and it's doing that at an absurd amount, or at an absurd speed. So please tell me a joke about the sun and the moon. Here's a classic sun and moon joke for you. Why did the moon visit the sun one day? To see how the other half shines. Beautiful. Love it. So now that everything is working, we can run GenAI Perf profile to benchmark the throughput and latency that we are seeing on this. So whenever I'm running GenAI Perf, I establish the input sequence length, output sequence length, the model, and a couple other configurations that I want to profile. So let me run. So what it's doing right now is it is sending 40 benchmark requests using synthetic prompts that GenAI Perf generates to directly to the model, and it's measuring the token generation speed, the throughput, and the time to first token, the latency, as well as the end-to-end latency. How long does it take for the entire prompt to be completely done? So we can see here that provides these metrics in a nice table for us. And we can see the output token throughput is about 750 tokens per second, which is, that's just an absurd amount of computation, like I mentioned, running on this H100. So lots of throughput that we can see. And we can also see the request latency. Now, keep in mind, this is the end-to-end latency of about 4 seconds to generate the answer to our synthetic prompts. So very easy to get up and running with these benchmarks, and there's lots of ways you can configure it. You can introduce your own custom data sets on your benchmarks. So they're very flexible, and it really help you get an idea of the performance that you're seeing. Now, Anthony, I'll hand it over to you so you can talk a bit more about the different ways we can benchmark at the application level.
Great. Thanks, David. Yeah, so that's kind of looking at the inferencing engine and the throughput on that particular hardware. Now, if we kind of go to the other end of the scale, which is, what is the user experience? And I've got this application where I've got this chat kit integration, and this is a chat app. Users can ask questions about their orders, and it's using an MCP server in the background, so it's looking up this particular user's data and it's giving back information to them, and then they can have a conversation in here and hold a thread. So what I wanted to understand in this example is, how will this feel to the user? Like, what will the performance be to the user? And not just one user, because we can just test one at a time, but like, how does this actually happen when I've got 10 users or 50 users? So one of the tools I love for web testing is called Locust. This is a Python framework for testing. And I actually just asked GitHub Copilot to put together a set of test prompts to give the AI. So like, mine is related to stores and orders. So I said, can you come up with 50 starter prompts that are related to orders? And some of these are good prompts, some of these are not particularly useful or relevant, like people asking how they change their password or create an account or a loyalty program. Like, the AI is probably going to give a longer answer saying, I can't really help you with that. And so what we do in Locust is we create these users. And what you normally need to do is you need to space out the requests. So each user would wait a few seconds before asking a question. And then in code, you need to describe how to actually, use the application. And because I'm using ChatKit, there's like a standard API for ChatKit, which is like how you would start a thread. And so we issue this kind of thread creation request, and then we can start off with our conversation. We could also add some features in here, like adding images, or, we could do uploads and stuff like that. Now, what also is important, and the reason I'm doing this in code, is because the user has to log in first. So we have to log in and making a request to our login API. And then once we've done that, then we can make a request to the chat API. So I've kind of got this code. And then what I've done with this is I've put it into Azure Load Testing. Azure Load Testing supports both JMeter and Locust as a format. And then in Azure Load Testing, you can design basically say, here's my test script. This is what a test user looks like, but I actually want to run this test over a period of time. So I've run this test just for, I think this particular one, I think I actually ran for 24 hours. And what I was interested in particular is how does the performance measure over an entire day? And I've just done this with 5 users. And what we get in Azure load testing is we have 10 users it was. So I've got the number of users, and then I've also got this graph, which is, what is the total time to complete the test. So I can see how does that differ over the day. And one of the things you can do with Azure load testing is you can configure what are the server-side metrics you want to include in the test report. So here I've included the backend resource, so the actual AI Foundry instance, and then I've got some additional metrics. Some of the ones that Stephen was talking about, so the time to response and also the latency. So sometimes you might see a particular peak in the latency during the day, especially if you change the test or if you had like a surge of users or somebody else is actually using your application at the same time, which is what happened in that case. The other thing we can look at is the throughput, which is tokens per second. Even though that says Azure OpenAI, this can be for any model that's running in AI Foundry. That's just the name of the metric. Also, if you're running this in a virtual machine or you're using the example from the last session, which was a container app with a GPU attached, you can also include some additional metrics like what's the memory usage, CPU usage, and what's actually happening in the back end as well. So yeah, back to you, Steve.
Yep.
Cool. Okay, this is me. So in terms of like what you can actually do to try and improve performance, one of the easiest things everybody can do is they can look at the prompt. And if I compare 2 models, so I was comparing model A, model B, and I said, just test question, what is the capital of Azerbaijan? There's a 1-second answer and there's like a 100-second answer. And the reason is because in the 1-second answer, it responded with a single sentence, which is the capital is Baku. And the really, really long answer was 4 paragraphs about Baku in its cultural history, which is not what I asked. I asked, what is the capital? And one of the things you can do when you're comparing models is you want to look at and compare the length of the output. Because when Stephen was talking earlier about you've got the initial latency, the prefill, and then you've got the throughput after that, which is the actual text, the token generation. That's tokens per second. So the longer the answer, the longer it's going to take because the tokens per second is going to remain relatively the same. And so if a user asks a simple question and you've either configured the model, the prompt, or the settings so that it would give a longer answer, you will always see slower performance because it's going to take the LLM a lot longer to respond. So one of the things I really want everybody to think about is, in your prompt, were you specific about the expectation for the output? So like, I want you to give me a single word response. I only want a paragraph. Be concise or provide 5 bullet points. These are all kind of things you can include in your prompt to tell the LLM that you're expecting a concise answer. If you just ask it an open-ended question or in your system prompt, you haven't been specific about the format of the answer, it will tend to, especially for bigger models, they will tend to give you very long answers. And that will just naturally take longer because there's more tokens in the response. Also, the users might not want, in this case, I just wanted to know what is the capital of Azerbaijan. I didn't want 4 paragraphs about cultural history. So one thing you can do is in the prompt, you can set your expectations for the output context or the output size, and whether it is that actually you're looking for a concise answer. And if you are, you need to be specific about that. Next slide. Okay. The other thing we have is precision. If you're picking a model in AI Foundry, you really get the choice that's kind of done for you, especially if you're running it on smaller environments or smaller hardware, or you want something which is a bit more sort of optimized, then you can look at the actual precision of the model. When you think of AI inference, we're doing lots and lots of matrix calculations. Those are done on a processor, normally a GPU, and those numbers are normally floating point numbers. So there's a standard for that. 32-bit floating point number is like a sort of typical standard, and how most model weights are stored and also how they're calculated. CPU, well, processors themselves can actually do multiple calculations at once if the size of that number is smaller in terms of the actual bit length. And there are different methods we can use for doing this, but we call that precision. And so there are different formats. So floating point 16 is the standard and has been since the beginning of computing. Well, not quite, but BF16 is a newer format which gives you a broader range, but like fewer bits, which is like the point after the dot. And then we also have lots of smaller formats, so like 8 bits, 4 bits, 3 bits, and down, that can be used to represent the actual the weights as well as all the inference like calculations within the different layers. On the next slide. So the precision, so what you can do is you can take a model which has been put together for a higher precision format, so like FE32, for example, so for 32-bit floating point numbers, and we can actually boil that down through a process we'll talk about in a second, into smaller formats, so precision formats. The reason we do that, like I said, is because the actual processor can do more calculations at once if the format is smaller, because it can basically stuff them into a single register and do several calculations at once. Also because it uses less VRAM. So the actual model itself is smaller, but also the context that it needs to load into memory to do the calculations is smaller. And the difference is, for a 32-bit versus a 16 versus an 8, it is literally half the size or once again. And so we can basically go down all the way to a single bit. So something which was previously a 32-bit number, we can actually boil that down 32 times into a single bit. The downsides of this are on the next slide. I'll just give it another time as well, so we got a lot, heaps of time left. But so this process is kind of done using technical quantization, where actually the analogy I kind of gave was sort of JPEG images. If you're familiar with JPEG images, if you take them on a super high resolution SLR camera, or these days just a normal iPhone, you get this 30 megapixel image. Now the way you would compress down that image is by sort of like approximating the pixels, and then eventually you get something which could be down all the way to like 1 megapixel. So now it still looks like a picture, the same picture that you took, you'd recognize what it was, you just don't get the same level of detail. Quantization basically is a similar kind of concept, but we do it for model weights, and just actually entirely throughout the model. So the model itself, basically the format of that model is smaller. We're moving it to a smaller precision format. The consequence of that, I think on the next slide, next one. Oh, okay. Sorry, I'll just talk about the consequence of the quantization is that we have the model's accuracy is reduced. And on this point here, we've got basically looking at the comparison of the accuracy with the quantization formats. And kind of when we say the model's accuracy is reduced, because it's very appealing to say, okay, we could reduce a model size, we can increase the throughput, and we can also reduce the amount of VRAM that we need. Like that's very, very appealing, especially if it's like 4 times. So like, what is the downside of doing that? And the downside is that by reducing the precision, you reduce the accuracy of the model. It's quite hard to actually put your finger on exactly what the consequence of reducing the accuracy is. Because if you ask a question to the model and it can give you back an answer at a lesser accuracy, you might not get a sense of any differences, especially if the question you're asking is quite well known. Like the test question, like what is the capital of France, is like one that everyone always tests LLMs with. You can put it all the way down to a single bit and it'll probably give you the answer absolutely fine. The accuracy kind of comes up when we look at more complicated answers where you've got a lot more context, or where it's pulling something which is like lesser known, so there are not as strong weights for that particular question or that particular input. And how they would actually come across to the user is that the model doesn't seem to answer their question quite as well as it did at a higher precision format, or it's not able, or it starts to make mistakes. And where you'll see the mistakes is if you have a benchmark that's like a math test, for example, or a relevance test, you're looking at RAG, those quantized models will perform worse at those benchmarks. The difference is not enormous though, and so you kind of need to find a trade-off with the precision format that you want for quantization, as in terms of also what you want from the model accuracy.
All right, thank you, Anthony. So yeah, that was really great, covering the precision and quantization methods we have. So that can help improve the performance significantly. Of course, the hardware is at the core of all this, and the hardware that you're running on is going to have an incredibly massive performance, decrease or increase, depending on what you're using. So if you're running on, directly on CPU, your performance is probably not going to be very great. We looked at that in the last episode. PMLL ran an LLM using OLLAMA on a CPU, and it was, generating 1 token per 10 seconds. Whereas we just saw on the H100, I was running the Mistral model at about 750 tokens per second. And this just increases with every generation. The H100 was the generation before Blackwell. Now Blackwell is the latest generation, and we see a huge increase in performance on top of that. So the next we have, Vera Rubin coming out, and Feynman after that. So the performance that you're going to get out of the hardware is, just going to explode. So yeah, we'll see lots of significant increases there in the next few years. So what can we do whenever we're, configuring this model on the software side? Well, Anthony touched on the, prompt engineering, and how, a shorter input leads to faster prefill, leads to less latency. So another name for the size of your input is the input sequence length. This is the number of all of the tokens going into your prompt. So if you're using something like RAG or multimodal, where you're sending images and text, this is going to take all of that into account. So if I upload it, PDF to the model, the input sequence length is all of the tokens that come out of that PDF, as well as the instructions that I give the model. The output sequence length is what the model actually produces. So we can sort of tune for performance by constructing our input sequence lengths in a very efficient way. So what we generally see is that with a higher input sequence length, we see higher time to first token, or latency. Now this graph, it only shows up to 600 tokens for an input sequence length, but if you're using, like long context or large context or multimodal use cases, this would go probably to the thousands. And we see a general increase in latency over time, latency over the course of your input sequence length increasing. So in general, a better input, shorter input sequence length that still provides the same results will get you a faster response. Now, I touched on this a bit earlier with batching. So if you remember, batching is essentially processing multiple prompts on the same GPU at the same time. And we see in general that the more batch, or like the larger batch size, the more prompts you fit into a single batch, the higher throughput you're going to get. Now, of course, this kind of tapers out the larger your batch size is, because you're essentially exhausting the resources on the GPU. If you extend this and go to a batch size of something crazy like 10,000, it's not going to be much better than what you're seeing here. because your GPU is already exhausted with that batch. So keep in mind that there is a trade-off here between the latency and the throughput. So better batch size doesn't always mean, better performance overall. It just means that you can get higher throughput. And if throughput is all you care about, then that's great. Increase your batch size, sure. But in the real world, you're probably going to care about both latency and throughput, and the real batch size that you want to use is something that you'll just have to sort of figure out yourself, mess around with, test it out, and find out what feels right for your model. Now in concurrency, we see a similar thing. So concurrency is essentially the amount of processes that your engine is running at the same time. So we can see across different numbers of threads, 1, 4, 8, 16, that might be too small to read coming across on the screen, but we see that in general, the larger prompt length or larger input sequence length, as I was calling it, leads to a longer or more throughput during the decode phase. So whenever you have higher concurrency in general, you're going to see higher throughput because you're running more processes. But again, you might need to test it out to figure out what feels right for your model. And of course, talking about the hardware, Azure and NVIDIA Neotron together provide optimized performance at every layer of your AI stack. So whether you're using Azure VMs or Azure ML or AI Foundry, you're going to get hardware that is optimized for AI ML. And this is really going to help decrease that latency and increase the performance that you're seeing. So not only does NVIDIA provide the GPUs to run these models, but NVIDIA Neotron provides the models themselves. So if you go into Azure AI Foundry, we have 3 Neotron models that are ready to go in just a few clicks. The Neotron Nano 9B, the Neotron Super 49B, and the Neotron Nano 8B vision learning are all accessible on AI Foundry. So this provides optimized performance at the AI software, AI weights, AI architecture layer. And a bit more about NVIDIA Neotron. So as you're experimenting and deploying on Azure, keep this in mind because NVIDIA Neotron provides a whole slew of resources that help you tune and refine your models and improve performance. It's not just a family of models like I was showing on the last slide, just the model names, but it's models, data, techniques, tools, recipes that are all entirely open source. So this is a really great way to get your hands dirty, figure out how these models work, learn about the architecture, and optimize them for performance. Neotron uses a lot of unique techniques like neural architecture search and a hybrid transformer Mamba architecture that allow it to get up to 6 times the throughput of similarly sized models. And that's what we see with the Neotron Nano 9B V2 model on AI Foundry. So a couple of I see we're at time, so I'll go a bit more quickly here. But there are a couple advanced techniques which really, I think, are just completely fascinating and so cool. And I encourage you all to try these out. So the first is something called speculative decoding. And this really helps you bump up your throughput by essentially running 2 models at the same time. So you have a target model, which is, the models that we're familiar, with, like GPT-OSS, Llama, Neotron, etc. So those are your larger target models. But when you're running speculative decoding, you actually are also running a second smaller draft model, which is maybe 1 billion or 2 parameters. And that's generating tokens much more quickly so that the target model doesn't have to generate all these tokens, but essentially approves them and accepts these tokens generated by the smaller draft model. So we see a very significant increase in throughput whenever you're using this method. Speculative decoding is pretty awesome. And so this is an example of like what you might see, the difference in throughput whenever you're using speculative decoding off versus on. And I encourage you to look at NVIDIA's speculative decoding models. NVIDIA makes a lot of the draft models, which are the smaller, really quick models that go out ahead of the larger target models and generate these tokens more quickly. So lots of really cool stuff here. And we see really big performance increases whenever we're using this. So for example, with Llama 3.2 1B, up to a 2.9 times increase in performance when using speculative decoding versus just without the draft model. Now, the last advanced topic I want to talk about here is something called disaggregated inference. This is very, very cool. Again, I encourage you to look into this stuff more. I think it's incredibly fascinating. So with traditional serving, which is what we've been talking about so far, you are passing your prefill and your decode processes. Remember, I talked about those at the beginning. These are running on the same GPU, right? Your prefill generates, it loads your prompt, encodes it, generates that first token. Then the decode stage comes into play and generates all of the remaining tokens. Now, whenever we're running this on a traditional setup, both these processes are running on the same GPU. The prefill is a bit more compute bound because of all of the matrix multiplication you have to do. The decode process is more memory bound because of all of the reads and writes you're doing to this KV cache. Now, whenever you go and examine disaggregated serving, you're actually running the prefill and the decode processes on separate GPUs. So what happens is your input comes in, the prefill handles all of the encoding and setting up of the KV cache, which is then handed to your decode hardware, which handles the remaining tokens. And this is great because once this is handling the decode tokens, this hardware up here handling the prefill is ready to start receiving more inputs and more prompts. So we see significant performance increases when using disaggregated serving. And I encourage you to check out NVIDIA Dynamo. This is our disaggregated serving framework. And it has a lot of, it's open source as well. It has a lot of really cool tools that, if you don't want to use disaggregated serving, you can also use it with traditional serving. But yeah, definitely check out NVIDIA Dynamo. One of the big features that NVIDIA Dynamo has is called KV cache aware routing. So as your KV cache is stored on different hardware, Dynamo will actually figure out what's the best hardware that I can route this prompt to. And this helps drive down latency and increase throughput even more quickly than what we were seeing before. So there's a lot of performance boost that you can see with this. And it's really just another fascinating area that is helping to drive up inference throughput and drive down latency. Yep. So yeah, that was pretty much it. I encourage you all to go and try it out yourself. I have a QR code here linking to one of Microsoft's documentation sites, and it instructs you on how to deploy a model from AI Foundry. So definitely go and get your hands dirty, test out all this stuff that you learned, and let us know how it goes.
Thanks everybody for your time today. Yeah, I really enjoyed the session, and if you do have any questions in the chat. Also, this is part of a series, so at the end we'll kind of share a link to some upcoming episodes. We'll be putting up one again next month. So yeah, thank you so much, Stephen, for bringing your expertise to this as well. We've learned a lot of really cutting edge techniques as well that we can apply to some of our model infrastructure. So yeah, thank you very much.
Of course. Thank you, everyone.
All right.
Thank you all for joining, and thanks again to our speakers. This session is part of a series. To register for future shows and watch past episodes on demand, you can follow the link on the screen or in the chat. We're always looking to improve our sessions and your experience. If you have any feedback for us, we would love to hear what you have to say. You can find that link on the screen or in the chat. And we'll see you at the next one.